This conference will now be recorded.
Okay, welcome everyone. We're kind of jumping around into what I wanted to cover today. So the agenda for today was revisiting the immersion cooling specification that was published in January when when the immersion requirements Rev 2 was published. So what I've done here is I've taken the contents of 7.6 here in this document and I've put it out into the diagram. So we'll go through that and we'll check if anything's changed given what we've been through in the last few months. And then, time permitting, there's another item here that has been on the agenda for the last couple of meetings that we haven't got around to, is talking about secondary hardware management protocols and how far we should go with those. All right, so without further ado, let me jump back into the diagram. So over here on this tab, the immersion cooling tab. So like I said, I took the contents of the document and I put them into our common format here with the resources and the interconnects. So what I'll do is I'll just give a quick overview of this for people who aren't familiar with that document. So it's the typical outline that we have been before. We've got the facilities water system, we've got the return supply, temp, pressure, flow valve, leading into the CDU, and then on the CDU you've got obviously the sensors for the FWS that I just mentioned and the TCS. The difference here is that the document actually specifies the names for these sensors. So you've got TCS capacity percentage, TCS supply temp, TCS return temp, FWS. You can see here, including flow in litre per second. You have something to note here on the CDU. The document mentions a TCS pump action, which in previous calls we've been referring to that as the control method. So it's telling the CDU how to perform control, whether that was based on pressure or a differential temperature, all those different control methods that we've previously discussed. So that's a slight difference there that we need to reconcile, because that naming is different to what we've been talking about with respect to the other scenarios and topologies. Okay, let me scroll down into the TCS. So what I haven't specified here is obviously in between that CDU, you could also have another embedded CDU, or rack CDU is the terminology we've used. You could obviously have a main CDU and then an embedded CDU on the edge of the tank. I mean, there's all different types of layouts I've seen for immersion cooling. So there is that possibility to have, a CDU chain here. I've just left it out for brevity here. And again, on the inputs and outputs, you've got your temperature, pressure, flow rates. Okay, and that leads us into the immersion cooling unit itself. So what we were discussing at the start, we hadn't specified that there's two different types here. So we've got this. My first question is, we've got this as an immersion cooling unit. So that is supposed to represent any of the, I guess, tank-based units that you might have. So is that generic enough to use, considering what we discussed earlier with the open bath versus the enclosed chassis, or would they be distinct cooling unit types that we need to separate out?
So make in that diagram that we just modified for the tank
Yeah.
immersion, the arrows are only connected to the room CDU.
Okay.
So I mean, I don't have an opinion. It's just I think we need to have the same message in both in this diagram and the other master diagram. So either we connect the open bath immersion tank to a rack CDU and a room CDU, or it will be just has to be the same message. I mean, whatever the decision is.
Okay. So the let me go back to that. So we look at this. So an open bath is the open bath topology is that it has an external CDU. Is that what we're specifying, saying?
Well, yeah, that's what was specified. So maybe people with tank immersion in a better position to answer that. If the tank will be, if there is a possibility for the tank to be connected to a rack CDU or not, or to a secondary CDU.
Uh, this is by no means complete. So if this is missing connections, then I'll add them in because I'm not the SME, but my understanding was this embedded CDU could or rack or embedded CDU could refer to one that was, at the end of the system. Like if you had a open bath and then on the end you had one end you had power distribution to the devices, the other end you might have the actual CDU as part of the chassis, if that makes sense. So I think that this is missing that interconnect to an embedded CDU. So I will add that in. So unless anyone disagrees with my amateur interpretation of those devices. So let me just put that note in there. Okay. So, I mean, in having said that, is there any, apart from what is installed or what is cooled in these systems, is there any other major difference that would dictate that they are not representable as a single cooling unit?
Sorry, but could you repeat the question if possible?
Oh, okay. Let me jump back here. So you look at this immersion cooling unit, this resource. So what this is when you're doing the hardware management, you would say, I've got an open bath, which is a cooling unit. So I would choose that it's an immersion cooling unit. Then I would specify, make, model, etc. If I was doing a enclosed chassis unit, I would also call it an immersion cooling unit, and then I would specify the same make, model. So my question is there anything materially different between the open bath and the enclosed chassis immersion that would dictate that they need separate resource objects? Or they're just a immersion cooling unit? Now, I don't believe there is, because they're both going to have the same superset or subset of these resources, but it, let me bring up the document. So this document, right? Let me see if I can show you the document in the example in the document. So there is.
Is it the difference where an enclosed chassis is typically one server, or maybe I'm misstating that, and a bath might have multiple devices in it?
Yes, that's
Yeah.
right. So with a chassis level immersion, you would have same form factor as air cooled rack, and that will means each chassis will have one server, while for tank immersion, you will have a number of servers in the same enclosure, in the same tank. And therefore, for chassis immersion, you will have sensors per chassis, while for the tank immersion, you will have sensors for the whole tank.
Okay, I think we can cover that, but let me capture that. Let me capture what you just said, because that's a very good distinction. So, enclose chassis. Each each server chassis is its own bath. Is called separately. Is that what we're saying?
Yes.
So is enclosed the correct terminology?
Enclosed chassis. Yeah.
And would have its own set of sensors. So it's conceptually similar to what you have with cold plate, except that it's physically in a bath, right?
Correct. Yeah.
Okay. All right.
The chassis is the tank, right? For
Okay.
that, if you would look at it, that each unit would be immersed, and the chassis is the tank for the enclosed chassis. While for the open bath, you have several servers, right? There are several IT equipment in there.
Yeah, it's essentially almost like an ITE rack on its side that you put stuff in from the top. But
Yep.
That's an oversimplification because they're normally specialized sleds or something, right? So, okay, awesome. So then for open bath, multiple servers in the same tank. So that means that the current document as it is tailored to around open bath because it explicitly mentions you need to have, at minimum, you have to have sensors at the input and at the output of the tank. But I guess you could extend that to say, like you said, if each chassis is a tank, that's still valid. You've just got multiple server level tanks, right? Okay, so it's just really where the server relationship is. You either have one to many from the CDU, or you have the CDU is one to tank, and then the tank is one to many. So okay, all right. So let's move back to this. So let's see if this is still representative of both those scenarios. So if in that particular case, let's go through the enclosed chassis first. So you've got the CDU coming down feeding a immersion cooling unit, and it would be.
You mean in terms of component distributors or PCBA suppliers?
Is that a comment or a background? Okay. So so what we're saying is for the enclosed chassis, the CDU would be feeding multiple immersion cooling units, and each of these immersion cooling unit is a server chassis essentially.
Yes, that's correct. And they are feeding, connected hydraulically to the CDU through a manifold.
Uh-huh.
So it is similar as the cold plate rack.
Oh, okay, that manifold has come back into the picture again. Okay, I got it. Okay, so in terms of hardware management in this enclosed chassis environment, is the only way to get the temperature or any kind of reading from the immersed chassis from the BMC? So you have to.
Yes, should be.
Okay, so it's identical to cold plate in that
Y-
regard as well. Okay.
Yeah.
Okay, I was not. So we can. There's no problem with covering that scenario because we do the same thing with cold plate. The only difference here is that, and I'll update the diagram to reflect this, is that the chassis is slightly different because it's actually the chassis surrounding a server is an immersion cooling unit itself. It's a tank. So I will get that updated. Okay, and then so if we're looking at the open bath scenario, you have a CDU feeding into the open bath, the immersion cooling unit, and then that would then contain another chassis, which is where the IT equipment is mounted, which I haven't. Let me put that on here. So we'd have, in that scenario, you would have chassis, IT. So you would have bunch of chassis. That is the equipment being cooled. All right, so that one there is for open bath. I will, as usual, I'll clean this up afterwards. I'm just trying to get all this captured as we go along. Where are we from? And obviously that chassis collection will then have a bunch of chassis which is representing your ITE equipment, but I won't bother putting the chassis in now just to save some time. Okay, so all right, let's just continue on. Is that clear? Is there any questions about what I just rapidly rearranged? Okay, good. So going back to the specifications from the current document, so you've got the immersion cooling unit, you've got, let's go and look on the right here, you've got a controls collection, so you've got power control, and in the document it's specifying that there should be a power action, which is essentially an EPO just shut off the input power into the tank. So this DLQ power action is if you turn that off, it will shut down all the incoming power to the ITE. And that's obviously a safety measure when you have a overheating condition. Okay, so then if we follow this along, and again, this has to be cleaned up to be proper redfish resources, but the idea is to capture what's going on. So yeah, you can tell it to turn off all the incoming power to the IT equipment. On the out of all the IT power supplies, you want to have an aggregate power input, and that's what this sensor here represents, the DLQ power input. So at any time you can tell how much power is going into the IT equipment. Okay, the other sensors here, we obviously have the input and output temperature that I discussed. So for an open bath that's at the bottom and at the top. For a enclosed chassis is that's not going to be possible, is it? Because it's a manifold fed. So for an enclosed chassis, we're only going to be able to get the sensors from the BMC, so the CPU temp or the GPU temp. Is that accurate statement? Given that the manifold is, there's no manifold level censoring that we know of. That one. The other sensors here, we have the dielectric level, and these are separated into two separate types of sensors here. The level and level state. So the level state is just a binary. It's either good or it's not. Same with quality state. So the quality of the liquid is either good or not. And then these other two sensors here, the level and the quality, are optional analog sensors. So, if you have a level, some kind of level sensor in there, you can have a 0 to 100% for the level. For the quality, the same. You can have, if you've got sensors in there that can measure the DLQ quality, you can have a 0 to 100 representation as well. Obviously, the fallback here is just these states. It's either good or it's not. Good or it's not. Okay. Those. And the reason, just if I remember correctly, the reason that there's two different representations of those two properties is that I think specifically for DLQ quality, there wasn't necessarily any sensors that were cheap or reliable enough to do a quality state for the DLQ. And same principle applied for the level. If you wanted to implement level, you could. Otherwise, you could just specify that it's over a threshold or not, good or not. Okay. The two over here, environmetrics, thermal metrics, those are just summary resources that you can reference from the main cooling unit. And the power meter here, this one is tied into a pump. So if the immersion cooling unit implements a pump, then you can grab how much power that actual pump, or how much ancillary power is being used by to keep the immersion cooling unit running, as opposed to the power delivered to the cooled equipment. Okay, let me stop there and see if there's any questions or concerns. All right, so it must be 100% accurate. Good to know. Okay, so what I think that since we've already
Hey,
covered
Nick.
CPUs. Yep,
So,
sorry.
sorry to interrupt. My
Yep,
mute is
no,
actually
please
taking
do.
a while. I was actually wondering about this enclosed chassis immersion cooling, about the interface, because what I've heard is that everything is actually exposed to be a BMC. So no way of actually of having, let's say, a dedicated interface for the telemetry or the metrics or the management, if I understood correctly. And I guess that this goes to Mustafa.
Okay, so I hinted at this earlier. So this enclosed chassis immersion cooling, we would have to use the same system topology that
Yes, cold
we
plate.
developed for cold plate. So you're going to have to use the same aggregation of the BMCs back into the Redfish service, the Redfish aggregator service, and then your CDU can then reference that to make any decisions.
Okay, I see. Yeah, I haven't seen this diagram.
Yep. So I will add this new scenario into this diagram as well that it applies to enclosed chassis immersion cooling.
Cool.
Because
Thank you.
as far as I can tell, it's identical, except this bit here is not via a couple of connectors. The whole thing is submerged or I don't know if it's submerged or you just got an enclosed chassis that you just fill up with coolant. I'd love to see how that actually looks in real life. So
cool. Yeah, that's it. Yeah, thank you.
sorry, Mustafa, is that what you're essentially doing? Is having a chassis that's fluid proof and you just fill it up with, or am I just
Coolant?
simplifying it?
Yes, yeah, that's right. So, yeah, it is basically, as Jessica said, so it is a tank, let's call it tank immersion, but each tank can take one server. And each tank will have like its own sensors, leak detection, temperatures, and you name it.
Okay. So each tank would have its own hardware management interface, or is it just going to be the BMC like shown on here? Let me.
No, I think both. It will
Okay.
it can be both.
So are these the same alignment as you would get in the open bath, i.e. that they're standing? If you're thinking about a traditional service chassis, they're standing on their end, like they're taller than they
Yes.
are wide.
Yeah.
Okay.
It is
So
exactly like air cooling in terms of management and control.
your cold is coming in the bottom again, and your outlet is at the
Bottom
top.
or top, yeah, it's both scenarios.
Okay. And is it a custom server or is it just a standard server that you just install in the
It is
individual tank?
it's standard service.
Okay. So sorry, I'm going to capture this so I can make sense of it later. So if we call that sorry for my vast simplification, but it's going to go in there, and then you're going to have we'll call that outlet to CDU. Oh, actually, to manifold, right? Inlet from fold. And you're saying that it is possible for the tank to have its own controller, its own hardware management interface? Mustafa?
Oops, sorry, I was muted.
Yeah.
Yes.
All right, so we can have a scenario where the actual tank has its own hardware management interface, plus within the server we've also got the BMC. So let me just grab one of those. I'll grab one of those and pop that in there. Oh, seriously, the lag is killing me. Come on, go over there. Okay, so we could essentially have a scenario where you can use the BMC like the scenario with the cold plate, but you could also have a scenario where you can just draw on the hardware management interface for each of the individual tanks to get the same information.
Yeah.
And I think you were saying that this particular one here has its own leak detection, right? Temp. You have.
So, Mustafa, out of curiosity, are you using separate hardware management? So you are not using the BMC, rather using the hardware management and then connecting all of the sensors of the tank or the chassis to the hardware management, right?
Well, to be honest, can you say it again? So it is, we have our control board. It is, so the sensors can be read in both routes really.
Okay.
That's yeah.
Yeah. Yeah. So rather than using the BMC server on the server itself, you are having a separate control board for the chassis itself, right?
Correct. Yeah.
Okay. Okay. Great. Thank you.
Yeah. No problem.
Yeah. So sorry. So what parametrics or what sensors were on that control board? I got leak detection. Is it temp in and out?
Yeah.
Okay. And is there any flow rate or pressure or anything like that?
So yeah, there are. I mean, I guess what we put in here, are we putting a general thing, and then when people come to design their system, they will pick whatever they want, right? But what we put in here is what we are enabling people to be read through Redfish, right?
Correct. So we try to capture what
So we
is
can put all
possible
the
now and what is
parameters.
possible in the future, so that the
Yeah.
model
Yeah,
will
so we can put the
accommodate.
parameters in, and then with time, or whoever thinks there is a need for that sensor or the other, they can have it, right?
Correct.
Yeah. So you'll have this. You'll have pumps health. You will have what else? Coolant level.
Okay. Yep. So exactly like the open bath.
Yeah.
All right. Cool.
Yeah, so I mean that's what I'm saying. Let's have the same of what we
Okay.
put for the open bath, and it will be kind of customized for people whatever they want to use.
Yeah. Okay. I'll just put that shortcut then. All right. That makes sense because it's essentially the same model. You just got a lot of smaller tanks.
Yeah.
So, okay. That's great because that means it fits in. You're just changing where the one-to-many relationship is, like I said earlier. All right, that's a fantastic addition. I was not personally aware of that particular topology. Okay. So like I said, I will redo one of these for immersion cooling because we can use the same aggregator topology for we can use the same topology for the immersion cooling for the enclosed chassis. I don't see. I'll have to redo the diagrams and stuff, but I don't see any changes to the resources or the collections or the links because we're just doing a slightly different
Yeah, and
makeup
if you
of where they sit.
I mean, if you want us to review it later offline, we're happy to do so.
Yep. What happen is I'll clean all this up, and then it will be available in this diagram, and you can look at it, and we can also come back in a later meeting and spend 10 minutes just checking that it was all captured correctly. But I'm not overly concerned. Like I said, the basics are there. We just got to make sure we got the right capturing of it. All right. Okay, fantastic. Are there any more questions, queries, concerns about immersion cooling? Let me flick back to it. So just one more question about the enclosed chassis. Earlier I was talking about the ITE power and the emergency power off, the cutoff in the event of a overheating scenario. So is that a similar concept with the enclosed chassis? Is that something that that controller within each tank is capable of, turning the incoming power off to the server, or how does that work?
I think it works similar to what would you put to a cold plate,
Okay.
more than the tank itself. I mean, more than tank submersion. Because we will use same PDUs as
Yeah.
normal PDUs, air cooled, or no, well, they're not called air cooled, but you know what I mean, for the vertical PDUs, and they will have similar control, similar things, and they all will be customized based on the customer requirements.
Yeah. So that's actually raises a good point. When we were discussing cold plate, we talked about the feedback loop and the control loop with the CDU. So if any one server or GPU or cooling target starts to heat up, it will increase the flow rate, to try and compensate to make sure it's within bounds. But there was I don't recall any mention in cold plate about what happens if the fluid is in an overheating scenario. Like, is there a safety for cold plate if the whole fluid gets above a safe temperature? I don't recall us discussing that. Does anyone on the call know what happens with cold plate if everything gets too hot, or there's some other kind of?
Well, the standard server
breakdown?
scenario, regardless of the cooling methodology, is you monitor the die temperatures of all the critical chips, and there's a fallback for dropping clock speeds and voltages to the chips if they start to get up to, say, 125 degrees C or so. And then if that doesn't help, then there's a dramatic fallback for clock speed and voltage. And if that still doesn't work, then you power it off to protect the chip. So regardless of what the cooling does, it's got a self-protection mechanism in it.
Yeah, so that's just pretty much standard. It's the same with air cooled. It just starts to throttle back until it has a thermal shutdown. But I was more referring to, is there any danger with the cooling fluid itself if the CDU? I'm guessing the CDU itself has got its own internal cutoffs where it'll just stop. Because we had the scenario with immersion cooling that it has to be able to cut the power, going into the tank if there's any kind of overheating condition, because there are.
And I would
dielectric
also think
fluids
that,
that break down, etc., and all the
yep.
rest of it.
And I also think that boiling the glycol mix in a
Yes.
cold plate would be a really bad idea too.
Yeah, Victor here from Cool IT was going to chime in.
Yeah.
So generally speaking, we've gone through a bunch of experiments where we boil coolant within cold plates and so forth, and exactly right, it gets pretty gnarly because the glycol has a different boiling point. So then your water vapor transmission losses increase, the viscosity of your coolant massively increases, and then you end up fouling any form of thin geometry within the cold plate itself. We have done some experiments with, jet cooled Alfrost, uh, our typical coolant, propylene glycol based. We've done Nalco and all sorts of stuff. And generally speaking, boiling is bad. So what we've done on our CDU side, Mick, you mentioned, shutting things down. We actually do the opposite. We try and keep the coolant flowing as rapidly as possible in order to mitigate that effect. And that's on top of the built-in safeties of the die temperatures that was discussed previously.
Yeah, and I'm assuming none of these scenarios arrive quickly, so there should be alarms going off all over the place before you even get to anywhere near those points.
But just a question on
I would
that.
hope.
Will like will the server shut down itself? Why would we shut down the PDU? Because the server will either regulate itself if the temperature goes up and it will throttle, or it will shut down itself. So why we are shutting down the PDU for it? Because it will regulate itself.
I think for the immersion cooling case, it was stopping any kind of heat in the tank once it reached a critical point. So it just cuts all power to all the IT equipment in the open bath. Because I'm not sure of the exact reason, but it's just like it's the equivalent of the big red button, right? It's the EPO.
So in air cooled rack, is there a control like that? Is there a control where if the server temperatures goes up to beyond critical, the PDUs shut down? Is this
Wow,
a practice?
a PDU in that scenario has its own thermal limits after which it will stop working, right? It will, I don't know, it's 50 degrees or whatever it is, but I think these are getting a bit out of hand because in that case, if the room's that hot, someone's probably going to have to press the big red button. So it's I don't I think we covered off the cold plate. The only reason I'm mentioning it is because I was wondering if there was analogy in cold plate the same as there is in immersion cooling because of the different fluid properties, right? But it seems that the dielectric is needs more hand holding, needs more tender care. So I don't think we need to cover the existing air cooled critical failures.
Well, I mean, what I'm saying, if there is such a control in the air cooling, then I would suggest yes, we definitely need to consider that when we talk about like cold, well, direct on chip cooling or chassis level immersion. If there is no such a control, then we need to understand why with tanks immersion there is a requirement to shut down the PDU, because as far as I know the server will regulate itself, it will shut down itself if the temperature goes up. um, in probably tank immersion because it's open and all the servers are within the same environment within the same tank. Probably you need that. I don't know. I mean, people with tank immersion may be the best to answer that question. But for cold plate or for chassis level immersion, I don't see that requirements coming because every server is separated by itself. And
I guess that makes sense. But
particularly for chassis immersion, there is a dielectric loop and there's a water loop, like through the CDU. So if something happens to a specific server, that will not affect the other servers.
But you still have an issue if the dielectric coolant gets too hot, it can get dangerous. So if there is some problem with the electronics temperature management loop and the servers don't shut themselves down and you don't have enough cooling from the CDU, you could end up with a dangerous condition from overheating the dielectric. So
I see what you're
have,
saying.
so I think having some kind of a fail-safe mechanism, at least described in this, wouldn't be a bad idea, so that you could have an upper temperature limit for the dielectric coolant, and if you exceed that temperature, then you would kill the power to everything in the tank.
So you're saying basically we enable it, and if people want to apply it, there is a way to apply it because it is enabled in our discussion, which will be utilized in Redfish. Is that what you're saying, Mike?
Yes, and we could suggest it and not necessarily require it, or strongly suggest it as a safety mechanism or something.
Yeah,
I
and
don't recall the wording exactly. I think it was. Let me see if it was a hard requirement. High safety requirement. So yeah, it's listed as a high safety requirement here in this immersion cooling. So it's the power action, and it's related to the quality as well, because obviously if your quality breaks down, then that can have all kinds of impacts on how the dielectric works. And I think from memory, and again, I'm not an expert on this, is with 100 kilowatt tanks, and if you have some kind of contaminant, that you could quite quickly get I'm assuming quite quickly get a runaway situation where you have to cut the power or bad things happen. So
Just to add something else to the conversation here. One of the main reasons to actually, let's say, and I'm actually with Michael on this, to have a strong recommendation on implementing this kind of fail-safe is that the operating temperatures on liquid are actually higher than on an air server. And the other thing is that the air server is able to regulate by itself. I mean, it's able to control the fans by itself. Not only that, but the margin that you have with those higher temperatures is actually less. You will see a spike or an increase in temperature that maybe the server itself with the PMC or with the let's say cutoff algorithms that has already implemented for air in the BMC is not enough to safely shut down that server. So this is why most of the time is actually safer to operate at a PDU level. Um, so I don't know what do you think about that, but yeah, I mean I agree with with most of the, let's say, opinions stated here. Just to add a couple of more.
Cool. So I'm fine with that. It's just a question then. Are we controlling the whole PDU? So will you shut down the whole PDU for the whole service, or will you have a control per
Rather,
out?
I would say that rather it would be, let's say, recommended to have a per outlet control to be able to somehow discriminate which server is actually going to be shut down, or let's say group of outlets if this is redundant.
Yeah, because there's no point to shut down the whole, all the servers if there's a problem with one server.
Well, I guess that it depends on the scenario. In your case, I guess that it doesn't make any sense. Depending on the scenario for immersion cooling, maybe it makes sense to actually stop the whole tank operation, shutting down all of the servers.
Okay, yeah, that makes sense. Yeah.
And just to add to that too, we should just make sure that we keep it as a recommendation. We highlight the safety issues that can be exposed, but then mostly keep it as a recommendation because some customers are experimenting with much higher temperatures than we talk about here. It's not this year or next year, but they're looking 3 to 5 years out, and the 5 year and more out guys are looking at really high temperatures, 70, 80 Celsius. And some are even looking at temperatures beyond that.
I would like to see that happening, Eric.
Yeah.
It's actually really high temperatures.
Yeah, they're trying to figure out if it's doable and experiment with it, but for what we're doing here, I think we just need to make sure we make it a recommendation and not a requirement. I know that a lot of customers see big differences there.
Okay, to be clear, that is outside the scope of this work stream. This work stream is to make sure it can happen, and from a hardware management perspective, whether or not it does happen or is recommended, that's up to the sub project. So
Okay.
in this case, it would be revisions to the immersion cooling document, which is that sub project. Like,
Okay,
yeah,
that's fine.
Yeah,
because
I'm actually
currently
waiting for that to start again.
it's currently a critical red high safety requirement in the immersion cooling document. But like I said, our job here is to make sure it can be implemented. You know, whether it is or whether it's required or whether you can ignore it, that's a sub project. So if you do have
Yeah,
concerns
so
about it,
I will add
suggest
an interface
join
for that. I will
I
add an
suggest
interface for that. Yeah.
should go and join the immersion cooling project call if it's of a concern to you the way it's currently stated. Okay, that's the top of the hour. So again, great session. We always end up on different tangents, so I like that. I think there was a lot captured today, a lot more than I thought there would be with immersion cooling. So that's again fantastic. I will get this cleaned up. Let me just stop the recorder now. So I'm going to end the formal part of this, and then if there's anything else off the record, I'm happy to hang around and